Hey there, coming at you from West Virginia, as you can clearly tell. All right, I believe it is time for Joke of the Day because it is the best part of the day. How do you find Will Smith in the snow? You look for their fresh prints. All right, well, let's just walk our way into the probability of the union of two events. Thank you, JD, for that background music. And Isaac for the laugh track. So anyways, when we're dealing with the union of two events, I've got a picture description of what happens here. So let's take the blue circle here as representing an event that we want to happen, or one of the events that we want to happen. So this will be the probability of that particular event happening. But we are looking at another event happening, so this red circle represents the probability of the second event happening. Now notice there's a little bit of an overlap of these two events happening. Right here in this center is where the two events are overlapping. So we call that the intersection of the probability of the two events. So if we want the probability of the union of the two events, in other words, we want the probability of the two events happening together, we need to take out the overlap because we don't want the overlap to be counted twice. Because what happens is, if we only take the probability of the blue event happening plus the probability of the red event happening, notice that the probability of the blue event happening takes into account this centerpiece. The probability of the red event happening takes into account the centerpiece a second time. We don't want to count that overlapping part twice. So we need to take out that overlap part so that it only gets counted once. And this is our formula for the probability of the union of two events. Take each event, add their probabilities together, and take out the probability of the overlap. Now, if the two events are mutually exclusive, that means that they have no outcomes in common. In other words, there will not be any overlap. And if there is no overlap, then it stands to reason that here would be the probability of the first event, and here would be the probability of the second event. And so if there is no overlap, then this does not need to be taken out. And so this part of the equation is now gone. So the probability of the union of the two events would be just simply the probability of the two events added together. So let's take this concept that we see right here and let's work with it in a few examples. The first example says I've got a single card that is drawn from a standard 52 card deck. And I do have a standard 52 card deck right here with me to illustrate. In that 52 card deck, we do need to understand that we have 4 suits and 2 of them are black. Let's get this out of here. I'm going to write this up at the top so that we understand. 2 of those suits are black, so I've got clubs and I've got spades that are black. And then I've got 2 suits, and let me show you that. Here are the spades. And here are the clubs. And I've got 2 suits that are red. I've got diamonds and I've got hearts that are red. So I've got my diamonds and my hearts. Now we've talked about this before, that if there's 52 cards in the deck and there's 4 suits, that means there's 13 of these, 13 of these. There's going to be 13 of the clubs. And there's going to be 13 of the spades. And then we discussed, oh dear, the under the world sea is just going crazy. We discussed as well that within each suit there are 13 cards. Notice that they go from 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, Jack, Queen, King, and Ace. So within each suit, I've got 3 face cards, an ace, and then 2 through 10 within each suit. So I have my ace, my king, queen, jack, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. Idea being that I've got 3 face cards in each suit. With that knowledge, let's take a look at this example one more time. So it says I'm drawing a single card from that standard 52 card deck We want to know what's the probability that it is either a face card or a red card. In other words, I'm looking for the union of those two events. Either or means both of them can happen. One of them can happen, one of the other can happen, but I'm looking for the entirety of the two. So I'm looking for the probability that I get that face card as well as the probability of, that's not the probability of a fur, that's the probability of a face card unioned with the probability of a red card. So that means I need to deal with the probability of having a face card and that probability alone. In addition to the probability of getting a red card, but there's going to be an overlap with that because there will be some red cards that are face cards. And they'll get counted once here, they'll get counted again here. I don't want them counted twice. So I need to take out that overlap of that intersection of face card with a red card. So let's take a look at this probability of getting a face card. Now remember, probability, once again, is going to be success over total. So the successful ways to get face cards, recall that there are 3 face cards within each suit. So I've got 3 here, 3 here, 3 here, 3 here. That means 3, 6, 9, 12 successful ways to get a face card. And what's my total? Well, there's 52 cards in the deck, so it's 12 out of 52. Now the probability of a red card, successful ways to get a red card, here are my 2 ways to pull a red card. 13 out of diamonds, 13 out of hearts. That's 26 total successful ways to get that red card out of 52 total cards. But remember, I need to take out the overlap where I've got face cards within these. So I've got 3 face cards here in diamonds, 3 face cards here in hearts. So I need to take out those 6 repeated cards, the intersection of the 2. Now I'm going to take and add these fractions and subtract them. In order to add and subtract fractions, we need common denominators, which are already there. So I can add those numerators and subtract. So 12 plus 26 is going to be 38. 38 minus 6 is going to be 32. So that's 32 out of 52. And always simplify a fraction if you can. And a 4 will go into both of those. 4 goes into 32 8 times, and 4 goes into 52 13 times. And so I get a 8 out of 13. I'm very sorry. 8 out of 13 is going to be the probability that within that deck I pull out either a face card or a red card, the combination. All right, so let's take a look at a couple of other examples dealing with this concept of the union of a couple of events, taking out that complement. So in this example, notice that I'm not given anything necessarily to deal with. I don't have cards that I'm working with, not rolling dice or anything like this. I'm just simply told that I know that whatever this event A is, whatever this event B is, I know that the probability of event B occurring is 0.45, which would be 45% of the time. I know that the probability of the union of them happening, A or B, either one, is 0.6, which would be 60%. I know that the intersection of the two, the overlap of the two, is going to be 0.20, which is 20% of the time. So I want to find the probability of just A happening. Well, we can use algebra in order to figure this out because I do have my formula that says the probability of that union is going to be the probability of one plus the probability of the other minus the probability of the intersection. Now, I do know the union is 60, 0.60 that is, 60%. I do not know the probability of A. That's what I'm looking for. So I'm going to leave it in there. I do know that the probability of B is 0.45, 45%. And I do know that the intersection is 0.20. So here I can just basically do algebra in order to figure it out. Because I know that 0.45 minus 0.20 is going to be 0.25. And then I know in order to get that 0.25 to the other side, I need to subtract 0.25 from both sides. And I know that 0.60, I'm running out of room. 0.60 minus 0.25 is going to be 0.35. And And so that will give me the probability of A. In other words, A will occur 35% of the time. So you can see, as long as you know this formula, which is a very handy formula, you can plug your numbers in and then you can just work that equation as needed using algebra rules. So let's take one last example here, and this is an application of being able to use that idea of the overlap and taking that overlap out whenever you want to do the union of an event. So this says that we're looking at this chart here that compares annual income to the amount of time that a consumer spends shopping on the internet. And it says, if we use this chart, we want to know what's the probability that the consumer that we selected randomly, either spends 10 or more hours per month shopping on the internet, or has an annual income that's between $40,000 and $60,000. We want the probability of that happening. Now remember, it's stated that this is an either-or situation. The idea of or tells me that it's this kind of union event. So what's going to happen here, and I'm going to erase this top example just to give me more room to write. I'm fearful that if I write along the side here, it's all going to get scrunched up and you're not going to be able to see anything. So enjoy the fishies in the back, enjoy the scenery while I clear this up. Lovely undersea world here. So again, what I'm going to do here is I'm going to say the probability that the consumer spends 10 or more hours shopping on the internet, or has an annual income between 40 and 60,000, so between 40 to 60. The probability of that union is going to be the probability of 10 or more hours plus the probability that the income is between 40 and 60. But remember, there's some overlap there, because here's my 10 or more hours and that total is right here. But here's my 40 to 60. There's an overlap right here of 160 people. And I want to take those 160 people. I don't want to count them twice. I want to count them once. They'll get counted once here. They'll get counted again here. So I need to take one of them out. That's why I'm taking out this overlap of the 10 or more and between 40 and 60. Take that overlap out. So the union that I'm looking for, the union of 10 or more hours and $40,000 to $60,000 income, is the probability of those who shop 10 or more hours. Here's all the people that shop 10 or more hours. Now be very careful, because this 192 is 192 people who shop 10 or more hours and have an income of greater than 60,000. 10 or more hours and $40,000 to $60,000 income. 10 or more hours and income of less than $40,000. So I want everybody that shops 10 or more hours, that's a total of 480 people, out of 1,600 total people here. These are the totals of all the people who have an income greater than 60,000. This is the total of all the people who have an income between 40 and 60,000. This is the total of all the people who have an income of less than 40,000. This is the total of all the people who shop 10 or more hours. This is the total of all the people who shop 3 to 9 hours. This is the total of all the people who shop 0 to 2 hours. And if you add all these up, you get 1,600. If you add all these up, you get 1,600. So there's 1,600 total people in this group that I'm dealing with. So when I look at the probability that I've got people who shop 10 or more hours, it's 480 people out of 1,600 people. That's the probability of selecting someone who shops 10 or more hours. Now the probability of selecting someone who has an income between $40,000 and $60,000, there's all of them, but that's 512 people out of my total of 1,600 people. So 512, again, out of 1,600 people. Now recall, I need to take out that overlap. So these people who shop 10 or more hours intersect with those who have the income of $40,000 to $60,000. There's 160 people that are in both of those categories. I need to take out those 160 people out of 1,600 people. So now that I've got those common denominators all the way across, I'm just going to simply add and subtract those numerators, because that's what it takes to add and subtract fractions. You keep that denominator, you work those numerators. So 480 plus 512 minus 160 will give me 832. Yes, 832. And now I'm going to simplify that fraction of 832 divided by 1600. And since this was typically reported in decimals, I'm going to go ahead and report it as a decimal as 0.52. And that means that 52% of the people will either shop 10 or more hours or have an annual income between $40,000 and $60,000. So I hope that helps you with the idea of the union of a couple of probabilities. And let's go back again. I think that Venn diagram from the very beginning just really seals it for us and helps us to understand how this formula works and why the formula is the way that it is. Here's our formula, and understand, if I want the probability of the two together, I need to take out this overlap because it's getting counted twice. It's getting counted once here in the probability of the event. It's getting counted again here in the probability of the other event. I need to take that overlap out because I don't want it to be counted twice. So I hope that helps. Have a great day.